Okay, so now let's first introduce what functional data analysis is. So here is the one examples, classic functional data examples. This is so this is Jim Ramsey. If you know Jim Ramsey is kind of the founder of functional data analysis research area. So he designed one experiment. Basically, he wrote FDA, the three letters, with a pen, and he put a monitor in the nib of the pen, and then recorded the trace how he wrote FDA the three letters. He wrote these three letters 20 times, and he recorded the position of the nib of the pen on a piece of paper. So so we have like x axis and y axis of this the position of the pen when he wrote FDA letters. Okay, so naturally the position of the pen, the x-axis and y-axis of the position of the pen will be a function of time, right? So what we can do is that we can put this separately. So we have two graphs. The top graph is the x-axis of the pen over time. So this x-axis is the time now, and the bottom graph is the y-axis of the pen over time, okay, in milliseconds. So in these examples, we have so for each, we have two variables, the x-axis of the pen and the y-axis of the pen. And we have 20 replications. So in each of these graphs, we have 20 curves. And also, we have 14,001 time points for the observations. So here I have two dimensions data. So this is a classic example for functional data because it represents many unique features for functional data. So first, generally for functional data, so functional data is kind of a fancy name for curves. Okay, basically for functional data analysis, we often dealing with curves. Like here, we have 20 curves. Okay, the reason we call it functional data is because we think these curves, it can be treated as a function of time, right? So therefore we call this functional data. So you can see here for each of these curves, the trend are pretty complex, right? It's kind of going up and down, right? So it's not like just a linear function, lines, straight lines. Okay, and also, so in each of these curves, we have a lot of measurements, a lot of observations for each curve. So here, what the special feature for functional data is that we instead of look at each observation at each time point as one single variables, we will treat the whole curve as one data point. So we call this as a functional data. Okay, so this is the special perspective for functional data analysis. So each curve will be one single functional data. So in this case here, so we have 20 replications with 14 and 1 observations. Instead of to treat this as all this as over 20,000 observations, we will just treat this here as 20 data points. Okay, so here we only have 20 curves, we only have 20 functional data. Okay, so this is one unique perspective for functional data. And so when we treat this functional data as a whole curve, then we can now look at the trend of the curve or the feature of the curve. For example, like if we look at these curves more closely, like we look at between 650 to 1000 milliseconds, we can see the curve is going up and down and up, right? So we have these features. So what we can do is that we can find these features by looking at these replicates together. Generally, these curves will share some similar trends. So we want to get this trend um, and be able to summarize this trend and using this trend to doing some prediction. So the most important features for this curve is that you can see here this position of the pen actually are pretty smooth, right? So generally in real life, like most curves are very smooth, right? So therefore, we were using this smoothness feature for these curves to help us to recover this trend significantly. Okay. So as we just summarized, for functional data analysis, basically we are trying to analyze the curves, and the curve we treat all these curves as the functional data. So functional data analysis means the analysis of data that are functions or curves. But the domain of these functions don't have to be time. So it can also be like spatial locations or energy or the frequency of the some spectrum analysis. So functional data can have many applications. As long as you can plot the data as a curve, then we can use the functional data to to do the analysis. Okay, so here this example involved 20 replications. So we will treat these 20 replications as the realization of one single stochastic process, and we will find the feature for this stochastic process. So generally, because the trend of this curve are complex, so it cannot be easily described by mathematical formula. For example, for these curves, it's hard to give a parametric form for these curves. Therefore, we will using some non-parametric way to characterize these curves. And also, the variations among these replications is hard to describe. So you may see here, like for example, the peak has some wide range and so on. But like how can we characterize or quantify these variations is kind of a central area for this functional data analysis. So here is a summary of this about the characteristics about functional data. So first, this data are measured of a smooth process over time or some other domains, and we generally will make no parametric assumption on this process. And we are interested to look at the variation of this process and also the relationship of this process to some other response variables. Generally, this data has a high resolutions and a low noise, but now the more recent work on functional data analysis actually are able to handle very sparse resolutions and very high noise. I will give you one examples later on. Okay. So the functional data analysis is first given by Ramsey in 1991, and it now applied in many applications. So we have several computing methodologies in functional data analysis, and we will give like kind of I think most methodologies actually are very similar. So we will cover most methodologies in functional analysis, and so generally the functional data is a little bit complex. So it's different from the linear regression. So it requires some thoughts and some checking. Get some graph of the data, so it's a little bit tricky. But if you get used to it, it should be pretty easy to use. So in this course, we will focus on what can functional data analysis do. I will give you some applications about functional data analysis, and I will show you some R code. How can we doing the functional data analysis in R? We also have Ramsey also developed a MATLAB package for functional data analysis. So if you get used to MATLAB, you feel free to use MATLAB. We will use R in this course because R is free and it's public available. So hopefully after this course, you are able to understand how FDA working, and you are able to interpret the result for FDA. So we will not cover theoretical foundation for functional analysis in this course because of limited time. So for this course, we need it will be useful if you know multiple linear regression. So it will be helpful if you have working on R before. But if you don't know R before, it is fine. I will give you the R code. So I will also give you the R examples, and you can just follow the examples. It should be easy to run. So we will using some matrix in this course, but are very limited. So if you so I think generally should be easy to follow. Okay, I will make it simple. So we will there's one classic book. This kind of Bible in this area called Functional Data Analysis, written by Ramsey and Silverman. Is this called this book? On the left side, it is a very well written book. It's very easy to read. I highly recommend you to read this book. Recently, Ramsey and his collaborators has written another book called Functional Data Analysis with R and MATLAB. So if you are new in this area, I recommend to start with the book on the right. The reason is because it gives the R code on the corresponding methodology, so it's easy to understand and follow. I have, as I just mentioned before the lectures, I have put all my lecture slides in my GitHub website, and you can download all my lecture slides and the computer code. And also I have the YouTube channel. I have posted my recorded lectures there. You can review the lectures after the short course. For FDA, we also Ramsey also has a website for functional data analysis, and you can download the R from the R website. You can Google R and you can find this website. Okay, so back to the functional data. So in these examples, because it's easy to measure the position of the pen, therefore we have a very high resolution. So, but generally, as we mentioned, there's we can accommodate data with a higher. Thank you. We can have accommodate the data with higher noise. For example, like this data are the average daily temperature in Vancouver over 1 year, and the bottom graph are the average are the precipitations of delay precipitations in Vancouver over 1 year. Okay, so you can see we are using this data as toy examples in this course a lot. So you can see here for temperature, the measurement is generally pretty accurate, but for the precipitation, you can see is has a high noise. But we are able to recover this smooth process under this noisy data. Another classic example is about the functional data is the growth curves. Okay, so here this to show you, I think it's the height of around 30 girls from age 1 to age 18. Okay, so this is their measurement are pretty accurate, but has a relatively low resolution. And also for this measurement, it's not equally spaced. Okay, so for example, here from age 2 to age 8, it measured once every year, and before age 2, from age 1 to age 2, it measured 4 times during the year, and after age 8, it will measure twice every year. So these observations are not equally spaced. The reason I mentioned this special feature is that because if you know time series analysis, for example, in time series analysis, generally the model requires the time point to be equally spaced. But for functional data, because we treat this curve as a function of time, therefore, actually it doesn't matter for us whether the time points are equally spaced or not. Okay, so we should be easy to handle these not equally spaced time points in functional data analysis. And also, a special feature for this growth curve is that this growth curve has to be strictly increasing, right? Cannot be decreasing. So therefore, we should handle these special feature constraints, monotone increasing constraints when we analyze this data. So this is can also be handled easily in functional data analysis. Yes.
Maybe I'm getting ahead of you, but so I see what I think is kind of interesting thing there is that the people that end up with the lower heights take longer to get there. So like the knee of the curve has kind of there's a function there. Would you be able to extract that from your data?
Yes. Yeah. This is actually a very good question. Like, so you can see here, in the functional data, we will treat the whole curve as one single curve, and after we get this curve, a nice thing is that we can look at the derivative of the function. Okay, so in calculus, we know that the derivative represents the rate of change of the process. So therefore, we are able to estimate the growth rate of the curve. So you can see here for this growth curve, it looks the trend are very similar, but if you look at the rate or the derivative of these curves, actually has a much larger variations. Okay, that's another kind of advantage for functional data analysis, is that we are able to handle the derivative or the rate of change. Okay. So this is another examples. This is the body fat percentage for 152 girls around the time before before the time before menage or after the menage. So you can see, I give these examples because you can see here the measurement actually are pretty sparse, right? So here each curve represents one girl, and you can see the measurement actually are not at the same time, right? So it's for each girls it may only have like 4 measurements, okay? On average is 6.4 measurements, okay? So you can see these measurements are sparse and irregular. So I want to show you that in functional data, actually we are able to handle this sparse data pretty easily now. Okay. Traditionally, functional data can only analyze high resolution data, but now we are able to analyze this sparse and irregular data pretty well.
Are there 162 cards in there, or you just selectively?
Yeah, I just selected maybe 10 girls here. I didn't plot all because it's hard to see everybody in one picture. Okay, so here is the goal of our course. So first I will show you how can we estimate the underlying functions without any parametric assumption. And then, as we said, we are also able to estimate the derivative of the functions. For instance, here, like this is the graph I show you about the body fat percentage. And so the red dots are the sparse data we have. So we are able to estimate these curves and behind this data, and also we are able to estimate the derivative of these curves as well. Okay, so the assumption in functional data. So first, in functional data, we generally assume the data coming from a smooth process. Okay, so we will using this smooth feature a lot in functional data, and so also the process should not easily be parameterized. For example, if you just see the trend is a clearly a linear trend or quadratic trend, then you don't need the functional data. The parametric, if the linear function can handle the data, it's usually the linear regression. But if you look at the trend is more complicated than the linear trend, you can I recommend you using functional data to it's more flexible. Okay, and also generally we require enough data to find the important features in the process. We require some repetitions in the process, and so we don't need the equally spaced or perfect measurements in the functional data. So here are some common sources for functional data. I mentioned a lot, like the functional data is generally we are dealing with curves. Actually, we can also dealing with the images. Okay, if you look at the images, they are functions of spatial locations, right? So actually we are able to handle these images as well. So we can see, like for example, in functional data analysis research, we have analyzed like EEG data and fMRI data a lot, and we have also working on the HIV antibodies change over time, and we have also working on the animal behavior, like the flying egg layers. And another important application is in the environment, because in the environment we have the air resolution, air pollutions monitored like every hours. So they are naturally functional data, and also the weather data as well for sure, and also like the traffic, for example. As long as they are measured over time, we are able to handle in the functional data analysis. So in economics or finance, when we have the stock market, the data over every day, we can use the functional data, and so there's also web data, like in the eBay auction prices and the Google trends. We can also use the functional data to analyze these curves or the images. Okay, so so we will try to answer the following questions in this course. So how can we go from the discrete measurements to a smooth curves? And how can we describe and summarize the random variations within these curves? And how can we decide the group of functional data are different, or the curves are different from different groups? And how can we relate the curves to other data? So these are the three big topics in this short course to cover. So firstly, we will going through some foundations, like how can we go from discrete measurement to the smooth curves, and then we will show you how can we explore curves or functional data using functional principal component analysis, and then we will analyze how can we dealing with the functional data with some other variables with the functional linear models. Okay, so this is the introduction for this functional data analysis.